Thank you. Thank you for the introduction. I'm glad to be here. Let me start my video here. Okay. Okay. Am I all set?
Yes, you are.
Yes, you're good.
Okay, thank you. So, hi everyone. Today I'm going to present on my latest research. My title is Empirical Inverse Transform Function for Ensemble Forecast Calibration. It's collaborative research from Dr. Laura Clement, George Yan, and Guido Cilavoni. And I am currently a PhD candidate from geography at Penn State. So, first off, I want to mention some of the collaboration agencies and funding agencies. This work has been funded by the NSF EarthCube and also collaborated with US Army Engineer Research Development Center, Rutgers University, and of course, I have to thank NCAR for providing awesome computing facilities. So, my talk today, I'm going to cover several topics. Here is a quick outline of my talk. So first, I'm going to talk a little bit about ensemble forecast and verification, because that is going to be the core of the following topics. Then I'm going to introduce the analog ensemble technique, which is important throughout the whole talk. And finally, I'm going to introduce the empirical inverse transform function and discuss how I do the ensemble calibration. Finally, I'll talk about the conclusions, and I welcome any questions. So to start off, just in case, so forecast, usually we have two types of forecast, which the first one is deterministic. The first figure on the left shows a single realization of the future state of the atmosphere. It gives you, let's say, a deterministic value for a specific location. This is an example for precipitation prediction. And there's another type which has an ensemble forecast. On the right, it shows you a range of different states of possible states of future atmospheric state. So the idea behind this is that, well, when a deterministic forecast only gives you one possible state, a range of them can give you a sense of how confident your prediction are. So sometimes people, you probably already seen researchers will say if the predictions ensembles member, if they tend to diverge, then they are not very sure of the prediction they're going to make. And so in terms of verification, it is important that you need to know, okay, when we shift to a forecast ensemble, are we gaining any benefit? Usually people would want to use ensemble forecast for different reasons, but typically ensemble forecast is usually more accurate than just one deterministic forecast. And the ensemble forecast can give you this sense of uncertainty. But how do we verify that? Well, first off, you can think of is you can fall back to the deterministic form by calculating a let's say a summarization of the ensemble. So that basically converts your ensemble back to a deterministic value. So you can use mean error, mean absolute error, and root mean square error. Mean error is usually good for detecting biases. Mean absolute error is a direct measure of the magnitude of the errors. And finally, if you are using RMSE, you are telling the loss function to kind of penalize more on the larger errors. So those are different choices typically in the realm of deterministic verification. So what about we want to stay as ensemble forecast? Well, there are many different types of verification metric to choose from. Today, I choose two metrics that are specifically related to the talk today. The first one is rank histogram, also referred to as the Talagram diagram. The second one is spread skill correlation. So let's dive in a little bit deeper. Rank histogram, first of all, it's a measure of how two distribution matches. So let's say if you have a forecast, if you have an ensemble forecast and you have observations, you want to see whether the forecasted distribution and the observed distribution actually match up. So to generate rank histogram, it usually requires a set of forecasts and observations. It doesn't work if you only have one ensemble. Let's say you only have one ensemble and one observation. You only have one prediction case. You cannot really generate rank histogram. You need to have, let's say, a prolonged time period and for a spatial domain to generate rank histogram. So the steps to generate rank histograms are, first, each of the members from the ensemble is first sorted from lowest to the highest, and those members are used as the cuts to define bins. So if you have 20 members, let's say, in an ensemble, you have 20 cuts, and then you have one observed value, and you figure out which bin does the observation belong to, and then you add one to the count associated with that bin. So you do this for a number of times. Then you have, for each bin, you'll have a count of how many observed values actually lies in within that bin. So a good rank histogram usually appears flat, and that signifies statistical consistency between the forecasted distribution and your observed distribution. So there are several figures in the middle, well, to the left, that gives you a visual aspect of how rank histogram looks like. So in the middle, which is rank uniformity, if a rank histogram appears flat, it basically tells you that the distribution, the forecasted distribution, the observed distribution matches pretty well. But in reality, that don't necessarily happen. So to the left is what it is called over dispersion. So here's a little bit mind exercise for you now. So if I ask you to only focus on the first bin to the left and the first bin to the right, there is a mean, there is a reference line which is the mean of the height, and basically it's telling you that there are too few observed values in the bins that are outside of this number, outside of the ensemble range. So basically what this is telling us is that this forecast ensemble is too wide, and it always covers observed values, and to the extent that it is similar to saying that an ensemble forecast is telling you that tomorrow's temperature can be anywhere from 0 to 100 degrees Celsius. Well, that is going to be true, but it's so widely dispersed. It of course covers the observed value, but it's barely useful. To another extreme, where is the right figure, the third figure on the second row, it is under dispersion, which is to the opposite to what we have just seen. So there are too many observed values that are outside of the ensemble. That is telling me that even our forecast ensemble says that for tomorrow's temperature, it's going to be between 28.1 to 28.5 degree. That seems like a very short range, but actually the observed value is never within that range. So the ensemble is being too confident and not very accurate. We also don't want that. So in order to see a good matching, we want to see a flat rank histogram. And to the top and to the bottom, there are also some cases you can use rank histogram to diagonalize biases. And this is also can use the similar tricks where we say, okay, which bin has too much or which bin has too few. So we can say, okay, whether our forecast is always high or always low. Second verification, and we're going to talk about today, is spread skill correlation. Spread here refers to the ensemble spread, which is basically the maximum of the member minus the minimum, or also called the range. Scale is the forecast scale, and it can be any scale of choice. Usually you can choose CRPS or RMSE. So here I'm showing you a figure comparing. This figure will come up later on in the presentation, but it shows you a comparison of spread scale correlation for 4 methods, for 4 technique. And the referential line is diagonal, and if a line is on the referential line, it means that the ensemble spread and the predictive scale are perfectly correlated. Why do we want them to be correlated? This is because we usually have the assumption that when we have a larger spread, the prediction is less confident, or we're uncertain. We're uncertain of what it's going to be. We are less confident in the prediction, and that assumption is based on this correlation. If an ensemble forecast has a high correlation, we can directly just calculate the spread of the ensemble, and then we have a sense of, okay, how big is the error, and how good is predictive scale without looking at the observation. But the bottom line is that this spread scale correlation is merely a measure of ensemble reliability rather than the actual forecast error. As you can see, it only tells you how good the correlation is, but it doesn't tells you the actual predictive scale. So that's one key point. There are much more information on this from down below is the reference. The chapter 8 talks about in depth talks about verification if you want more information. So coming back to ensemble prediction, analog ensemble is a technique that generates forecast ensembles from a single run of a deterministic NWP model. This is pretty powerful because instead of running a let's say Whorf model multiple times with different initialization or different boundary layer conditions, you can actually build upon an operational model with historical archive and generate ensemble based on that. So analog ensemble requires a historical archive of model forecast and the observations. So below the figure gives you shows you the schematic of how analog ensemble works. There are 4 steps. The first begins with let's say a current multivariate predictions from the NWP model. It can be a multivariate prediction for the next 24 hours. And then second, we search in our historical period, compare the current forecast with historical forecast and try to identify 4 most similar from the past. And then third, once we identify the most similar forecast, we then query our observation database and see what are the actual observed value from those days. And finally, we directly use observation values as our ensemble members. So there is a shift between the most similar forecast and using the associated observation as the ensemble. That is the key idea of analog ensemble. So this figure is adopted from Dr. Della Monica in the paper that first proposed analog ensemble. It is trying to predict wind speed, and to your far right, there is a black dot with a referential line. That is, let's say, that is the forecast, current forecast that we're trying to find analogs for. And then those labels shows you 9 analogs we find throughout this historical period. And if you can see, there are, because it's a multivariate forecast, the analogs are found using different weather variables, considering all of them together. It's not a univariate where you only want to find the most similar wind speed case, most similar temperature case. It's trying to find a globally similar throughout all the predictors. throughout all the weather variables. And you can see there are the most similar 1 to 3 to the right, and then the rest is mostly to the left. So Analog Ensemble currently has several years of development now, and its core algorithm right now is implemented in C++. If you're interested to check out that, the URL is over there. Right now it's parallelized with OpenMP and OpenMPI, so that it can be run on clusters and supercomputers. Also with file I/O, it works with grip2 via the support of easy codes from ECMWF. And of course, it works with netcdf4. And finally, I have been working on integrating Analog Ensemble with PyTorch to build a machine learning-based analog search algorithm. If you're interested, I would be happy to talk more about that. Analog Ensemble has also been ported to R. R is probably the most used API when for rapid research development. It allows for generation, verification, visualization, and because of its code base is in C++, it's very easy to do parallel multi-core parallelization even with R. So finally, it also has some preliminary API support for Python. But unfortunately, it's in its very early development stage, and currently it only supports post-processing ANN analog ensemble forecast from SDF file. So the reason why the Python API exists right now is mostly for me to post-processing the analog predictions generated from the C++ API on supercomputers. So throughout my research, I came upon a problem with analog ensemble and all the statistical ensemble. So coming back to the discussion of the over-dispersion and under-dispersion problem, here I'm showing you a rank histogram, actually several rank histogram that are generated using different ensemble members. So usually when you have, let's say, if you have a over-dispersed ensemble, the first thing people will think of is you have too many members in the ensemble, because when the more members you have, you tend to have a more variation and the spread is going to be larger. So usually people, if they have a over dispersed ensemble, one thing that they can do is reduce the number of ensemble members. But I once tested this idea of whether that's true for statistical ensemble, and it surprises me that here the histograms are showing for just temperature predictions, and when I reduce the number of ensemble members from 100 to only 10, the shape of the rank histogram remains similar, and it's a convex shape, so it's over dispersed. So it's always showing up as over dispersed, and that surprises me, and that also inspires me to come up with an additional correction method, calibration method that would help in this case. That's where eiTrans, also the empirical inverse transform function, comes into play. So the eiTrans function is an ensemble calibration technique inspired by the analog ensemble. The core idea is that the eiTrans seeks to find an optimal perturbation to ensemble members that would improve the reliability of forecast ensembles. So since just reducing the number of members won't help in terms of reliability, can we find out how to move each member a little bit, for example, to apply a small offset to each of the member so that our final predictions has a higher reliability? The following figure gives you an idea of how this workflow, how the workflow looks like. So first, it's just a regular rank histogram. This is a rank histogram with 20 members. As you can see there, each member is as a cat, and we have 21 bins. So this rank histogram shows that it's slightly over dispersed because we have too few members that is outside of the ensemble spread. And since it is a frequency histogram, we can also calculate cumulative probability. To the right, that's basically the cumulative probability calculated from the figure A. So if we want to achieve statistical consistency between the forecasted distribution and the observed distribution, we would like to calibrate the rank histogram so that it appears flat. And that equals to equally sampling from the vertical axis of figure B. So basically from 0 to 1, you want to see, okay, you want the rank histogram to be flat and with 20 members. So you want to find what are the optimal locations to sample in the probability space, and then you can map it back to the member rank space. So that's where you see the dashed line. But the problem right now is that the vertical dashed line does not overlap with your member rank. And that is expected because if they overlap, so basically if you look at the first member rank is here and the first dashed line is here, if they overlap, then if all the dashed line overlaps with the member rank, then it will generate a flat rank histogram. But currently it's not. And it is telling you that you want the first member to move a little bit to the right so that it incorporates more observed values in the first bin. Same for the second one, you want it to move to the right. And in general, you want to shrink this entire ensemble member so that we can achieve a flat rank histogram. So how does it look in histogram? Figure 3 gives you the basically it plots the same thing with the resampled location, but on the rank histogram. It is telling you that instead of using the original ensemble members, if you can use the dashed line as the bin cuts, you can actually generate a rank histogram that is going to be flat. But the idea is good. Figure D shows that if you actually use the dashed line to regrid or let's say rebin the rank histogram, that is what you get. And that looks pretty good, looks pretty promising. But how do you actually find out those locations? How do you actually find out how much you want to perturb each ensemble members? Because what you're seeing here on the x-axis is simply a rank. It's not a continuous value, but you need to find out what the actual value are. So there is one more problem that we actually don't have rank histogram when in the operational sense. It requires observations to generate rank histogram. So that is where analog ensemble comes to play. Instead of directly looking into the observation for the future forecast, which we don't have, we jump back into the most similar historical forecast and use the rank histogram from most similar forecast to correct the current forecast. So now, instead of looking at rank histogram for future, which we don't have, we can look at the rank histogram for the most similar historical forecast, which we're able to do it. So how does this work? So the idea seems pretty good, but how does it work in real case? I selected 6 locations for the US. The test period is a little bit more than 1.5 years, I guess, from 2017 to 2018, July 15th. And search period is a little bit more than 5 years, 6 years. And 6 locations containing 50 model grids. And I'm predicting surface temperature using 4 variables for analog searching. This is how it looks like. I compared 2 types of statistical ensemble. One is the analog ensemble, as I previously discussed, and another one is persistence. Persistence is merely generated from taking if you want 20 members, it takes 20 immediate historical observed values at that time point. So it just assumes the progress will remain. So typically you see for this type of problem, analog ensemble shows over dispersed, and the persistence shows an under dispersed case. And for eiTrans, it seems to be working pretty good at let's say Denver and New York City, Sacramento, and State College, showing a little bit of bias, resulting to a little bit of bias to the end. Miami is the one that's a little bit weird. It didn't quite correct pretty well for an ANEM, and it actually introduced a weird bump for persistence. Second looks at spread scale correlation. So again, we want the line to be as close to the diagonal line as possible. So here, basically we see two patterns where persistence is larger, and persistence larger error and analog is smaller error. But in general, if you're comparing the let's say the orange to the greenish color, orange is closer to the referential line, and the persistence with eiTrans is also closer, with the exception at Miami. Actually, you look at the reliability. Previously, the rank histogram for Miami wasn't very good. The reason for that is probably the ensemble per se has little space for improvement and calibration because it's already on the diagonal line. And another way to visualize this is to show the to break up into forecast lead time. On the horizontal axis shows you the forecast lead time by hour, and the vertical is temperature. Two lines are shown for each panel. One is the RMSE, one is the spread. So you want to see a the two lines overlap with each other so that we know that, okay, they have a higher correlation. So if you compare the first two columns, we see that after eiTrans calibration, the RMSE and the spread overlaps pretty close. And this difference in this improvement is more obvious when applied on persistence. Previously, you see the spread is smaller than the RMSE, so basically the ensemble has a smaller spread than the error. It's being too confident, but what eiTrans is doing is basically increase that spread, saying that you shouldn't be that confident. I'm going to increase the spread for it. For analog, it's kind of the reverse. For example, in this case at New York City, we have the RMSE slightly lower than the spread, and then eiTrans is able to see that we need to lower that spread. So this eiTrans is implemented in R, and the URLs is over there. Feel free to check it out. It's parallelization with OpenMP for ANEM generation, and it also has distributed computing capabilities for when actually doing the calibration. However, the limit right now is it only supports 125 concurrent cores due to the connection limit of R. I'm not using MPI. My experience with MPI, OpenMPI with R has been mixed, and sometimes there are weird situations that don't terminate. So I'm actually using socket, and R limits the number of concurrent connections for socket. So that is something to be done. So conclusions.
Hi, we mean we are a little bit over time.
Okay. I'm wrapping up. Conclusions. Forecast ensembles can be calibrated based on historical forecast ensembles, and also eiTrans is proposed to calibrate statistical ensembles. And finally, it has been found to work for both under-dispersive and over-dispersive ensembles. And that wraps up my presentation. And I think if you're interested in the analog ensemble, please check out the first URL. If you're interested in the eiTrans, please check out the second. And I'm always happy to talk with you about ideas. Yeah, thank you.